We're now ready to look at the derivatives of trig functions. One thing to remember is we are always dealing with radians when we have trig functions. Let's think of what the derivative of sine would look like. And as we look at the tangent at 0, the slope of the tangent is 1 and it's positive until we get to pi over 2 where it's 0, then it goes negative, and then 0, and then positive, and then 0, and then negative, and then 0 and positive, and so forth. So we can see that the derivative function would oscillate, and everywhere that the sine had a turning point, so at its max or its min, the derivative function would equal 0. So we see as we plot the derivative function that we are plotting a cosine function. So everywhere that the sine has a maximum, the cosine equals 0. You can see here where the sine is increasing, the cosine function is positive. Where the sine is decreasing, the cosine function is negative. So we've seen graphically that the derivative of sine is cosine. Let's go ahead and actually figure that out from the definition of derivative. So we want to apply this definition to the sine function. So we have the limit as h approaches 0 of the sine of x plus h minus the sine of x all over h. We see right here we have the sine of a sum. If you remember from trig, the sum formula for sine is the sine of the first angle cosine of the second plus cosine of the first sine of the second. So applying that identity here, we have the limit as h approaches 0 of sine x cosine h plus cosine x sine h, and then we still have this minus sine x, and that is over h. Now these two terms have a sine x in common, and so we're going to do two things. We are going to factor a sine x out of these two terms, and we have the limit of a sum, and we can write the sum of the limits. So we're going to have the limit as h approaches 0, factoring the sine x out of the two terms where it was in common. We're left with cosine h minus 1, and that is over h. And then we have plus the limit as h approaches 0. This is the term that's left. We have cosine x sine h over h. Now, as we're looking at this, both the sine x and the cosine x are not functions of h, and so we can move those outside of the limit. And so we would then have the sine x times the limit as h approaches 0 of cosine h minus 1 over h plus cosine x times the limit as h approaches 0 of sine h over h. So if we want to figure out what this derivative equals, we would need to know this limit and this limit. I'm going to give you both of these limits. The limit as theta approaches 0 of cosine theta minus 1 over theta equals 0, and the limit as theta approaches 0 sine theta over theta equals 1. Both of these limits are derived in the video following this video. But right now we're just going to use those then, and so this limit equals 0, and this limit equals 1, so this is 0, and we do have that the derivative of sine x equals cosine x. How about the derivative of cosine x? We can look at this graphically as well. We see that there are horizontal tangents at multiples of pi, and as we move along here, we start out with the derivative having a horizontal tangent at x equals 0, and then the function decreases, therefore it has a negative slope. So as we draw the derivative function here, we see that we have this trig function that is oscillating, but because it goes negative first, we see this is a reflection of a sine x graph. The derivative of cosine x is negative sine x. We can see that here as we look at the graph of the function and then look at the graph of the derivative. This can also then be derived from looking at the definition of derivative. From Trig, the sum formula for cosine is this one. And so let's go ahead and apply that here. That would leave us with the limit as h approaches 0 of the cosine of the first angle, cosine of the second, minus sine of the first, sine of the second. Then we also have minus cosine x, and that is over h. We are again going to factor out the common function. In this place it's a cosine. We could bring that actually outside of the limit, similar to what we did with sine. That would leave cosine h minus 1 over h, and then we have a difference here. Limit as h approaches 0. Oh, I didn't bring this function out in front. This would be sine x out in front and leave sine h over h here. So this one is 0, this one is 1, and therefore we are left with negative sine x. So the derivative of cosine is negative sine. Now, if we need the derivative of tangent, let's just think of tangent as sine over cosine, and we know the derivative of sine is cosine. The derivative of cosine is negative sine. We just found both of those out, so we could just use a quotient rule on this one. And so the derivative of tangent is going to equal bottom times the derivative of the top, and the derivative of sine is cosine, minus the top times the derivative of the bottom. The derivative of cosine is negative sine, all over the bottom squared. Okay, so the numerator becomes cosine squared x, negative times a negative, positive sine squared x. Aha, there's one of my favorite trig identities. The numerator is 1. Denominator is cosine squared x, so we could rewrite this as secant squared x. So the derivative of tangent equals secant squared x. If we want the derivatives of the other three reciprocal trig functions, here they are listed, and we could derive any of these by applying the quotient rule, because we have the derivatives of these, and so these are all 1 over those functions. So for example, I will do this for cosecant, and then you can see it would be similar for secant and cotangent. So if we want the derivative of cosecant, that is 1 over sine x. There's several ways we could do this, but let's just do this applying a quotient rule. So we've got bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. So we see we are left with negative cosine x over sine squared x, and that could be expressed as negative cosine x over sine x multiplied by 1 over sine x. And actually this is in the reverse order of how they're listed here. Here's our negative sine, and cosine x over sine x is cotangent, and 1 over sine x is cosecant. We could get these others similarly. And the one thing we need to remember is these are valid only when our x is in radians. Here's a little mnemonic that may help you remember these trig functions. The derivative of sine is cosine, is pretty easy to remember. Cosine negative sine, pretty easy to remember. A little mnemonic to help you with tangent, secant, cosecant, and cotangent. And that would be, you'd lean over and say, hey, psst, what's the derivative of tangent? So as we have this, our S, S, and T stand for secant, secant, and tangent. And the way this works is then the derivative of secant is secant tangent. The derivative of tangent is secant secant, or secant squared. Of course, these are of x or of theta. Now, the co-functions have negatives on them. Just like the derivative of cosine is negative sine, well, the derivatives of the co-functions are negative. The derivative of cosecant is negative cosecant cotangent. The derivative of cotangent is negative cosecant cosecant, or cosecant squared, functions of x.